In this final presentation on series resonance, we look at some examples that include looking at the bandwidth and the half-power frequencies. So here we have a circuit with a resistor, capacitor, and inductor connected to a voltage supply, and we want to determine the maximum power that's dissipated by the circuit. We know that the maximum power occurs when the system is at resonance, and at resonance the inductive reactance and the capacitive reactance are equal to one another, so the total impedance is just resistive. And so that means that the resistor in the circuit would get all of the voltage in the circuit, and so the maximum power can be found by taking the voltage of the source squared divided by the resistance. This is of course the real power. So this is 10 volts squared over 10 ohms, which gives me 100 watts. We can also determine the bandwidth at resonance, and so we know that the bandwidth is just the resistance in the circuit divided by the inductance. And so in this particular case, 10 ohms over 0.01 Henry gives us a bandwidth of 1,000 radians per second. So at this point, we haven't actually figured out what the resonance frequency is. We just know what the bandwidth is, or that range of where I'm going to have that half-power frequency. We can determine the half-power frequencies. So we know that the lower half-power frequency is just negative the resistance over twice the inductance plus the square root of the resistance squared over 4L squared plus 1 over LC. So I can plug those values in, making sure that I use Henry, which is the appropriate unit, and that I also use farads instead of microfarads. And when I do that, I get minus 500 in the first part, plus basically 10,000. And so my lower half-power frequency is 9,512 rads per second. I can calculate the upper half-power frequency going through the same process. I actually don't have to go through all this work because I realize that these two equations are exactly the same, but just a difference of a positive right here instead of a negative. So the upper half-power frequency would be positive 500 plus 10,012 rads per second, which is 10,512 rads per second. So I know the lower half-power frequency and the upper half-power frequency, and I also know what the bandwidth is. And if I take the difference between those two values, I should get what the actual bandwidth is. So let me go back for a second. If I take the difference between the upper frequency and the lower frequency, 10,500 minus 9,500, I'm going to get essentially that 1,000 bandwidth that I had earlier. I can determine the half-power frequencies by using an approximate method. And so the approximate method would be that I would have to figure out what is their actual resonance frequency. So I would plug in my inductance and my capacitance, and I find that the resonance frequency is 10,000 rads per second. Using the fact that the bandwidth is 1,000 rads per second, I can figure out what the upper and the lower half-power frequencies are by basically taking half of the bandwidth and subtracting it from the resonance frequency. So remember, the resonance frequency is where the maximum was, and then the bandwidth was the total width of between the two half-power frequencies. So if I take half of the bandwidth, which is 500, and I subtract it from what the resonance frequency is, I get 9,500. And if I do the same thing, but I add the half of the bandwidth, I get the upper half-power frequencies. And these are very close to what I had before. There's a couple of extra digits in the previous examples, but this is a good approximation for what the half-power frequencies are. Knowing the bandwidth and knowing the resonance frequency, if you take half the bandwidth and you add it to the resonance frequency, you'll get the upper half-power frequency, and then subtracting half of the bandwidth, you get the lower half-power frequency. we can solve for the current and the power dissipated at the lower half power frequency. So here we have to do a little bit of work. So the question is, just to show us that if we calculate what the power is when this circuit has a frequency that's at the lower half power frequency, we will actually get a power dissipated by this resistor that's half the maximum. So we know that at the lower half power frequency, that the frequency of my source would be set to 9,512 rads per second. I can determine what the impedance, what the impedance in my circuit is, and so I need to figure out what the reactive inductance is. So I would multiply that frequency that my source is now set at times my inductance, and I would get 95.12. And I can also figure out my capacitive reactance in the same fashion I've done before, and I get 105.13. So remember that in the if you go below the resonance frequency, and this is a frequency that's below the resonance frequency, that the capacitor dominates, and that's exactly what's happening here because it has more resistance than the inductive part. So the overall impedance in my circuit is the resistance plus the reactive components added together, and when I add these two components together, of course the capacitive part is negative, impedance part is positive, and I get a total impedance of 10 ohms minus 10 ohms of basically inductive reactance. I can convert that into polar form and figure out what the impedance is, and it's 14.14 ohms, phase angle of minus 45 degrees. I can determine what the total current in my circuit is for that particular impedance, which is 10 volts over phase angle of 0 over my impedance, and I get a current of 0.707 amps with a phase angle of 45 degrees. Using that particular maximum current in the circuit, I can determine what the power through that resistor would be, the average power in the circuit, and it would be the current squared times the resistance, and I end up getting 5 watts. And I realized that when I calculated what the maximum power was, it was 10, and so this does give you half the power. So when my circuit is set for a frequency that is in that lower half power frequency range, I indeed get half of the power in my circuit. Okay, so here we have another example. We have different information that's given to us. So we have a voltage supply, it's connected to a resistor, an inductor, and a capacitor. I don't know what the inductor value is, but I do know what the bandwidth of my circuit is. It's 10 kilohertz, and I know what the resonance frequency is in terms of hertz. So it's 600,000 hertz or 600 kilohertz. And we're asked to determine what is the inductance and what is the resistance. So the first thing is that I know that the resonance frequency, it can be written in terms of the inductance and the capacitance, and I have to make sure that I realize I have my value in terms of hertz or kilohertz, so I need to make sure I use the expression for frequency and not angular frequency. I can multiply both sides by 2 pi and then square both sides of the equation to get rid of the square root. And then I can cross multiply, bring the inductance to the top, and that 2 pi times the frequency squared to the bottom. And that will allow me to figure out what my inductance value is. So I know that my resonance frequency is 600,000 hertz. I need to make sure I convert everything into the correct units. And my capacitance is 220 picofarads. Pico is 10 to the minus 12, and I forgot the farad in here, but I've converted this into farads. And so I get an inductance of 3.2 times 10 to the minus 4 Henry, which can be written as 320 microhenry. I also know the bandwidth, and my bandwidth is just the resistance over the inductance. This is my bandwidth in radians per second, so I do have to be a little bit careful here. If I want to solve for my resistance, I could take the bandwidth that's given and multiply by the inductance. I have to make sure that I convert my bandwidth from, in this equation, because this is radians per second, into from hertz to radians per second. So I know that my bandwidth is 10,000 hertz. So if I multiply that by 2 pi, I will get the bandwidth in radians per second. And so my resistance would be 2 pi times 10,000, which will give me units of rads per second, multiplied by the inductance in terms of Henry, and I get a resistance of 20.1 ohms. So in this circuit, I have different information that's given. I'm using the fact that I know the bandwidth and I know the resonance frequency to calculate the resistance and the inductance. And I do have to be careful with my expressions and make sure that if I have hertz versus rads per second, that I use the appropriate equations. I can also find the current and the voltage across the inductor and the power at resonance. So before I go too far, I should figure out what the angular resonance frequency is. So it's 2 pi times the resonance frequency. So 2 pi times 600,000, right, gives me what the angular resonance frequency is. I know that at resonance, the total impedance in the circuit is all resistive. And so I can calculate what the current is. It would be the voltage of the source divided by the impedance. All of the impedance is resistive, so 20 millivolts over 20 ohms, both have phase angles of 0. This would give me 1 milliamp. If I want to know what the voltage across the inductor is, I have to calculate the inductive reactance, which would be the angular frequency times the inductance. I know the angular frequency, I know the inductance, I get 1,206 ohms. Much bigger inductive resistance or reactance as compared to the 20 ohm resistance. I can write down what the impedance is for the inductor. So because it is an inductor, it has a phase angle of 90. And then I can calculate what the voltage is across the inductor, which is just the current in the circuit, so the series circuit, times the impedance for the inductor, and I get 1,206 millivolts at a phase angle of 90 degrees. So I left it in millivolts on purpose so that we could see that even though we have 20 millivolts for the source, we can still have a really very large voltage across the inductor compared to that source. I can now figure out what the power is at resonance. So it would be the amplitude of the current squared times the resistance. The current is 1 milliamp, so I've converted that into amps. Square it times 20 gives me 2 times 10 to the minus 5 watts, or 20 microwatts. So we have very small numbers here. I mean, 20 millivolts is pretty small. 1 milliamp is a very small number. And my resistance is not very large, so I would expect that I would have a pretty small power in this circuit. So we can also find the approximate values for the half power frequencies, the lower frequency F1 and the upper frequency F2. And we can do that using the approximate method because we know what the bandwidth is and we know what the resonance frequency is. So the lower frequency is just going to be the resonance frequency subtracting off half of the bandwidth. So half of the bandwidth is 5 kilohertz. The resonance frequency is 600. So the lower frequency is going to be 595. And the upper frequency would be that if we took the resonance frequency and then we just added half of the bandwidth, it would give me 605. So that the difference between those frequencies gives me the bandwidth, which is 10 kilohertz, with the resonance frequency being right in the center. We can also use these results to determine the current in the circuit at the upper half power frequency and show that the power dissipated by the resistor at this frequency is half the power dissipated at resonance. So we know the frequency in the upper half power frequency is 605 kilohertz. We can calculate what the angular frequency is by multiplying by 2 pi. That allows us to determine the inductive reactance by multiplying the frequency times the inductance in our circuit, and we get 1,216 ohms. We can also calculate the capacitive reactance, which is 1 over the angular frequency times the capacitance, and we get 1,196 ohms. And notice here that we're in the upper half power frequency range, and so that means that the inductor is going to dominate, and it does. It has more reactance than the capacitive reactance. I can calculate the total impedance, which is just the resistance in the circuit, and then adding the reactive components together. When I add these together, inductive reactance is positive, capacitive reactance is negative, and that's the imaginary part. And so then I can calculate what I have the values in the rectangular form. I can calculate the impedance in the polar form. And then I can determine the current in the circuit by taking the voltage of the source and dividing by the total impedance in the circuit. And I end up getting 0.707 milliamps with a phase angle of minus 45 degrees. And so I can then use that information to calculate what the power is in the circuit. And the power would be the current squared times the resistance. The current has to be in amps, and then the resistance is 20 ohms. So I get, when I convert everything back, I would end up getting 10 times 10 to the minus 6 watts, which is 10 microwatts. And I realized that 10 microwatts is exactly half of the maximum power that we calculated early, because the maximum power was 20 microwatts. So just sort of in conclusion, these resonant circuits are important if we want to look at responses to our circuit, specifically if we're picking up signals. And so we'd like to have a certain range of frequencies that will work in our circuit, that we can pick up these these sources. And so we also are interested in, do we have a very sensitive curve? Is our bandwidth very small so that we really have to tune things? And we have a lot of power if we have a small bandwidth. Whereas as our bandwidth increases, our power can actually decrease depending on the circuit, that we have in terms of its resistance and so on. So these resonant circuits are actually important when we're building components that need to pick up signals, and that range of signals that we can actually pick up from our circuit.